Hi everybody, welcome back. This is another AP Physics 2 problem. Um, Actually, we're going to do this one slightly different. It's going to be a little bit more conceptual. Our goal is to get to one of the problems that we've looked at, but I want to go through electrostatic force, electric fields, and electric potential and go in there a little deeper so that we really understand the equations before we jump into the problem. So eventually, we're going to be getting to this problem where we look at um, these isolines of electric potential around two charges. But before we go there, we're going to dive a little bit deeper into some of the equations from our reference table and really understand what they mean. So I hope this helps. We're going to start right off with our first electricity formula. So I'll kind of cover up part of this. Electrostatic force, I should say. So let me write this down. Electrostatic force equals, they write it out as 1 over 4 pi epsilon naught, but we can also use that as K. Okay, and I'm also going to flip to the front of our reference table to remind you about that. We can see it right here, Coulomb's law, K, or that same 1 over 4 pi epsilon naught. So we kind of skip this 1 over 4 pi epsilon naught and just go straight to the 9 times 10 to the ninth. Okay, it's a little shorthand so that we don't have to keep writing that out every time. So let's go back. K Q1 Q2 over R squared. And let's think about that. This is a very specific formula. This is a formula for force between two charges, okay, at some distance apart. So this is not the equation you use for every single instance of electrostatic force. You have to have two charges. They might even call them point charges in the problem, okay? For now, we're going to kind of draw them as the same size, label them Q1 and Q2. Okay, where R is the distance between their centers. And hopefully that's making sense. So as I go through this, I think one thing that can become very confusing as we go through these equations is which Q are we talking about? So I'm going to try my best to use some colors here. So let's go with this Q1 will be our blue color, and I'll plug it into the equation as blue. And Q2 will be this pink color. All right. So this electrostatic force, K Q1 Q2 over R squared. Q1, and again, these might be, I don't mean to generalize. I'm going to draw them as attractive forces. The exact same vectors would be true if they were the same charges. In this case, I'm assuming that one of them's positive and one's negative. If they were both positive or both negative, these arrows would just be flipped around, but they would be the same. These are going to be our electrostatic forces. Blue arrow equal in length and magnitude to the pink arrow. So this might seem silly to you, but I'm going to say that our electrostatic force is equal to our other electrostatic force, which equals K Q1 Q2 all over R squared. Okay, and I'm going to write this for right now, maybe. So I'll just say that's why we usually call this just electrostatic force. I might even use a purple color here because both of them feel that same force. So hopefully that's really easy and straightforward. You might be like, why are you going so slow? I get that. I just want to take my time because as we get through this and we start working our way, we're going to see it depends. These other equations depend on which Q should we be plugging in here. Now, I folded that in half so we can really focus on the equations we're specifically looking at. Now, let's get to electric field strength. Okay. In some point in space, anywhere, Okay? Maybe everywhere in the room that you're sitting in, every single point in that room probably has some electric field strength in that location. It's probably varying. There might be some electric fields moving through that room, right? But in most of our problems, we're kind of looking at these isolated systems, and there could be some location, okay, that has an E here. I'm going to put, this is the electric field at a location. Okay. Now, what is the strength of that? Well, the strength of that electric field has to do with the force that some charge would feel there. The electrostatic force that some charge would feel there. So, let's now think, okay, well, what if I had a really big Q there? So let's put a large Q. This Q, a lot of charge here. If I put this right in this location, at that X in space, I'm going to put it right there. Maybe this feels a lot of force. Okay, I'll call this F. That's the force that Q feels when it's located there. Now let's take that out. Let's put in a different Q. So I'm going to draw a littler Q. This has a little bit of charge, so I'm writing that as a small q, and I'm going to put that at that location in space. Well, it's going to feel less force. And it's a little tiny, maybe you can't see it. So a big charge there would feel a lot of force, a littler charge there would feel less force, right? So hopefully that should make sense, right? We could think about that, well, maybe this electric field location is created by some other charge sitting here that's pushing those two Q's around. But maybe it's not. This E could be because of anything. So that location in space might have that electric field because there's some other charge here, right? And then when we put a charge here, it's feeling a force away. Maybe there's not a charge there. Maybe there's a whole line of charges, right? We've seen this with charged plates. Maybe there's a whole charged positive plate here. And so that when some charge is sitting here, in this case it would have to be, if this is a positive plate, a positive charge is sitting here, it's going to feel some force that way. When we're talking about this electric field strength, we have no idea what's causing that force. It could be anything. It could be an individual charge pushing on another charge. It could be a whole row of charges, or a plate, a positively charged plate, or anything like that. It could even be, I mean, it could be a series of, here's a charge, here's a charge, here's a charge, and the combination, each one of these is putting some force on some object here. The combination of those adds up to be one of these forces that we saw before, right? Because of those different charges, right? So we don't know what's creating the electric field here. All we know is that when I put a charge there, some charge Q, it feels some force. Okay? So in that case, I'm gonna say, if there is this Q here, that Q will feel this force. So I'm gonna rewrite that and say, the force that some Q feels. So here's the Q. This is the force that that Q feels. All right? Now, let's keep going. Let's think about this a little bit. Now, that might be the only way you use that equation. But if this electric field is caused by another charge, so a single point charge, well, then we know we have an equation for this Fe. We have an equation. If we're looking at an electric field caused by two charges, we have Fe. This is our equation for that force, the electrostatic force, when we have two charges. So we could plug that in here. Okay? Now watch what happens when we take our equation and plug it in here. Okay? we say the electric field, well, it's going to be K, our first Q, our second Q, divided by R squared divided by Q. And look what happens. Our Q's cancel out, specifically the Q that we're placing at this location. So if our Q's cancel out, then we're K. We only have our pink Q left, divided by R squared. Now, where do we see that? If you look on our equation sheet, we just found our third equation. Okay? This is KQ over R squared. There it is. Okay, what is that in relation to up here? So specifically, this third equation, our first equation is for two charges. Second equation could be any case where you have an electric field and some charge sitting in it, feeling a force. But our third equation, because we use this one, this third equation is again only for two charges. Okay? Or actually, I shouldn't say that. It's only for a point charge, right? Because look, this charge dropped out, right? So again, let me go back to this first picture. If I wanted to know what is the electric field at this location, at the blue Q, what's the electric field strength caused by this? We could use this equation. The electric field strength at the location where the blue Q is K pin Q over R squared. So we can use this if there was actually a charge there and it was actually feeling this force. Or we could do it in the hypothetical case. So here's the hypothetical case. We say, all right, I have some charge here. It has charge Q. There is no charge over here at some distance R. Oh, I wrote an R squared up here before. It's just, distance is just R. We square it over in our formula. So at this location, at this hypothetical location, if there was a charge there, what force would it feel? And let's get rid of the actual charge of the object I placed there, right? Because if I placed, and I'm going to actually just use part of my drawing from before, at that location, if I put a big Q there, that big Q would feel a lot of force. If I took that same location and I put a little Q there, it would feel less force. But the E at this location is not changing. The electric field strength caused by Q is not changing. That's what this is. This is the electric field strength caused by a single charge. So let me erase a little bit from this. And I'm going to say, this is for 2-point charges. This equation right here is for a single point charge. Okay? And your Q is the Q that's creating the electric field. Okay, let's go a little bit farther. Let's keep going with this. We're going to look at our potential energy due to the electric field. Okay? And we're going to look at why is it Q times delta V. Now we haven't seen delta V yet, or even electric potential. So let's dig in here a little bit more. Potential energy. Again, we're going to take these two charges. So we have a blue Q and a pink Q, Q1 and Q2. If this Q and this Q were touching each other, they would have no potential energy to move, right? Think of it as these things are being attracted towards each other, but they're already as close together as they can get. A lot of times when we talk about electric potential energy, we talk about there's a great analogy with gravitational potential energy, right? An object sitting on the floor, it's as low to the ground as it can get. It has zero gravitational potential energy. If we lift it up and we move it away, right? The farther away we move it, the more gravitational potential energy it gets. Well, the same is true here. So if some point later we were able to take this Q and we push it, push it, slide it over, and we get it some distance r away. All right, so maybe I'll do a little squiggly line, right? And we'll say our potential energy due to electric field here is 0. Well, what's our potential energy here? It's moved some distance r. Well, in gravitational potential energy, we think about, well, we're applying a force. So if I'm lifting my pencil, how am I lifting it at a constant speed? I must be applying a force up, right? That's equal and opposite to gravity. If it's a constant speed, right? We're in equilibrium. And I'm lifting it up, equal and opposite to gravity. And a force applied over a certain distance, that's a work. That's a change in energy. So we want to know how much work did we do to get our Q from here all the way over to here. So how much work did we do? Well, it depends on how much force we had to apply. And it depends on how far, I shouldn't put the FE yet, let's just say just whatever force we had to apply, and how far did we push it? Okay, in this case, I'm using R for that distance. And how much force did I have to apply? Well, I had to apply whatever the electrostatic force was. Okay, so that means we're applying the electrostatic force over that distance r. I hope you can start to see where this is going. All right, I'm getting somewhere. So at this new location, our new electrical potential energy is now going to be our electrostatic force times r, which means it's going to be K Q times Q, Q1, Q2, divided by r squared times r. Well, what happens here? Our r's cancel out, and our potential energy equals K Q1 Q2 all over r. And now let's think about this again. Let's go back to our larger Q and our smaller Q. In these cases, well, if I had a really big Q and I moved it from here and slid it out, it would be gaining more potential energy because it would require more force to move. And if I used my small little guy and I had to push him away, it would have less potential energy. Okay? So when we start looking at, electric fields and we're going to look at electric potential, sometimes we want to say, well, we have this Q. This Q is sitting here. What if I moved something from here to here? I don't know. Is it a big Q? Is it a small Q? There's actually no Q. It's a hypothetical. So we say, all right, in that case, I want to know, what would it be just because of this pink charge? We're going to divide out whatever this blue Q is. So we're going to take this and we're going to say, hey, it'd be really interesting to know how much energy per unit charge. And we're going to divide by that Q. So that means we have K, Q1, Q2, now just over R because we lost our R when we turned this into energy. But we're going to say we want to look at it per unit charge, so we don't care what the charge is of the thing we're moving. We only care about the difference caused in that potential energy based on the pink charge. okay? And we end up with K Q all over R. And this is, by definition, what we call potential energy. Or, sorry, not potential energy, electric potential, okay? This is our electric potential. That's, by definition, it's how much potential energy per unit charge that's placed in that electric field, okay? So by definition, that's what this equation is. This is actually the definition of that electric potential, okay? I hope you can see it. I know I'm kind of running out of space a little bit. I'm going to slide. By definition, if we take our V and cross multiply this, now we have V times Q equals electric potential energy. So V, and this is a really important point, V, and I'm going to point it out over here, is electric potential. U is potential energy. They're different. Electric potential is how much potential energy you have per unit charge that's placed in that electric field. So if this Q was a really big Q, that means you'd have a lot of potential energy, but your V would be the same. If it was a little Q, it'd be less potential energy, but per unit charge, V would be the same. Okay? And now, our last equation, V equals KQ over R, I hope you can see that that's actually right in here. V equals KQ over R. Okay? So, because in this equation, so this is our general equation. Okay, this is true always. This is true whether we have two plates. This is true whether we have, any amount of charges that are just creating electric fields and we're moving from, between two locations in that electric field. But this equation, because it has the way we derived it from using our potential energy here based on 2-point charges. Here we're looking at because of a point charge. So this equation is for, again, a single point. Now, to make this full circle, we want to see, well, why is V divided by R? Why is that electric field? Well, you can see the connection here, KQ over R, KQ over R squared. So there's a tight connection between our E and our V. So hope that helped laying out a little bit more about the electrostatic force, electric field strength, and electric potential. And actually, electric potential energy, right? Potential energy is different than electric potential. So what are some really important things to come out from this understanding? First off, you should understand that this first equation is for 2-point charges. This second equation is a definition. So this is like true all the time. Third equation, this is electric field created by this Q. All right, so that Q there is this single Q that we're talking about. We can have some location anywhere around here, above, below, any distance away. There's electric fields at all these points due to that charge. That's what this equation is all about. Here, we have a definition. This equation is true all the time. I'm going to put a star here. Okay? This equation, for a single point, we want to know the potential, electric potential around this charge. Just like before up here, this point is Q, and we can have an electric field at all locations around it. We can have an electric potential anywhere, here, here, here. Every single space around this has some potential caused by that. until we move far, 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 all the way away to infinity. At infinity, well, this bottom number becomes so gigantic that this limit goes to 0. So you have no more electric potential due to a point when you move infinitely far away. And this last equation here, this is mostly used when we're talking about parallel plates. Okay, maybe I'll just flip quickly over here. If we have some negative plate with a positive plate next to it, we know that the electric field strength everywhere within here is constant. Okay, so we actually have our electric fields parallel, and if they say these are, infinitely large plates, then it's parallel everywhere. If they have ends, there's this slight curving to these field lines on the edges, okay, which normally we kind of ignore those inconsistencies. But in the center, it's constant. Electric field strength here, 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 everywhere, it's the same. So in this case, when we're using this equation, your electric field in this location, every distance you change within here, okay, that's our delta R, will correspond with some change in our electric potential. Okay, so we'll have higher electric potential to the right near the positive plate, lower electric potential over here. That change in distance, divided into our change in potential energy, that's actually our electric field strength. So sometimes you'll see electric field strength written as volts per meter. That'll be a unit you see. Other times, if we think about it up here, electric field strength could also be considered how much force you feel per unit charge. So how much force we feel is in newtons per unit charge, coulombs. At the risk of, actually, maybe I'll stop here and I'll talk about the reason why that's true, and we'll go through a little bit of unit analysis for that, and then we'll split onto a third video, and then we'll talk about in that third video this problem and really understand what those isolines of electric potential are and what they mean. All right, so hopefully that was helpful. Check out the second video if you want to take a look a little bit deeper into these units and how could volts per meter be the same as newtons per coulomb. All right, take care. Hope it helped. Have a good one.